Welcome to another episode of James Explains, where today we're taking a further look into the last video I made, which was finding a solution to the folding puzzle. If you haven't seen the original video, click the card up in the corner or the link down in the description to go watch that first so that this video makes sense. The first thing I want to talk about is the last step of the previous video, where I took the output of the program I wrote and substituted letters for numbers to find all possible starting positions. As Yumel Hugo discovered, this is not actually the correct way to convert the output, but just by luck still managed to give me the 3 different answers I expected to find. The approach to convert from the numbers to the starting positions is to fill the letters out into the sheet in order from A to H in the positions indicated by the output of the program. Whilst it doesn't seem much of a difference, it means that 07251634 converts to AECGHDFB, not AHCFBGDE. So if you've been trying to solve all the permutations I listed in the last video, I'm sorry if you've been stuck on one. That's not actually possible. The next thing I want to dive deeper into for this video is for sheets larger than 2x4. And how this behaves with any given sheet size. The first step is to find a way to generalize the way we find which folds are on which edges. When we label all of our sections with face up or face down and which one's upside down too, you can see that the pattern repeats itself perfectly. So that means our edges should be fairly regular. To make it easier to picture these edges, we will look at just the face up, right way up sections, as these will have the same edges as the overall stack. Firstly, we can mark all the right edges of these sections, then all the left edges, and all the bottom edges, and finally the top edges. You can see that all the folds in the sheet can be lined up with at least one edge of the face up, right way up sheets. We can try to generalize this even further to make it so we can detect all edges using code. We can see from the previous image that right edges always fall between an odd numbered column on the left and an even numbered column on the right. Left edges fall within an even column to the left and odd one to the right. Bottom edges sit with an odd row above and an even row below, and top edges fall with an even row above and an odd row below. Knowing this, we can write our simulation to automatically find all folds and group them into the edge they fall on. So now that the code has been refactored to calculate a sheet of any size, let's have a look at some of the outputs that we are getting. For a 1x1 sheet, there's only one solution from one possible permutation. Sticking with the rule that the top left section has to stay at the top of the pile, we get the same values for a 1x2 sheet too. Once we get up by 1x3, we now have 2 possible solutions from 2 permutations of the stack order. At 1x4, we have 4 working solutions from 6 permutations, and 1x5 gives us 10 solutions from 24 permutations. Now that we have one form of sequence from our results, we can see that this can be found in the online encyclopedia of integer sequences, and it manages to return a result of sequence 682, which is about semi-meandering and stamp folding. This makes sense, because folding a ribbon of stamps is just like folding a 1-row sheet for the puzzle we've been given. Now that we have this, we can see what higher values would be, and as you can see, the values begin to climb very quickly as the size gets bigger. Next up, we have a 2x2 sheet. This has 2 possible solutions from 6 permutations of the stack. This gives us some more important information, because we know that a 2x2 and a 1x4 both have 4 sections and 6 permutations of the stack order, but they have a different number of possible solutions, so the shape of the sheet also makes a difference, not just the number of sections. The next is a 2x3 sheet, which has 10 solutions from 120 permutations. Then at 2x4, we have the answer from the previous video of 40 solutions from 5040 permutations. Slightly larger, at 3x3, we have 152 possible solutions from a little over 40,000 permutations. Going on to 2x5, we get 198 solutions from over 360,000 permutations. jumping from 10 sections in a 2x5 up to 12 sections in a 3x4, we get 1,696 solutions from nearly 40 million permutations. After 12 sections, we jump to 15 sections with a 3x5 sheet. This is where my simulation started to take a noticeable amount of time to generate the solutions. We get over 13,000 solutions from 1.2 billion permutations. The next size up is 16 sections in a 4x4 arrangement. This layout gives us 18,000 solutions and shows 2 billion permutations. However, this result did not make that much sense, as the number of permutations only rose slightly beyond the previous value. The giveaway is the size of the number 1.2 billion gets quite close to the maximum value for an integer in Java, so the value must have rolled over when counting permutations. Checking on the results, it appears that the previous permutation count was incorrect too. The values should look more like 87 billion and 1.3 trillion permutations for sheets of this size. As for sizes larger than that, this is where I draw the line at running the simulations. If you're aware of big O notation, the algorithm I wrote has an efficiency of n factorial, so the processing times expand massively as the sheet size increases. To give you an idea of what this looks like, we have the last two sizes we calculated, 15 sections in a 3x5 and 16 sections in a 4x4. The next sizes up are 20 sections in a 4x5 and 25 in a 5x5 arrangement. 15 sections required us to check 8.7 times 10 to the 10 permutations, and 16 sections required us checking 1.3 times 10 to the 12. To calculate 20 would require 1.2 times 10 to the 17, and 25 would require 6.2 times 10 to the 23 permutations. To put that in terms of time, it took roughly 2 hours to calculate the 3x5, a little over a day to calculate the 4x4. At this rate, the 4x5 would take 2.5 centuries, and the 5x5 would require 1.3 million millennia. Whilst there could be more efficient ways to run the simulations, these sort of sizes are well beyond the scope of the laptop I ran them on. One other interesting fact I found while searching the online encyclopedia of integer sequences is that this problem is very similar to the map folding problem. The difference being that in that problem, it's not limited to just the top left section of the top stack. It was interesting to read that for a stamp folding problem, an algorithm to calculate the number of solutions has been found, but requires exponentially increasing time as the size increases. For the map folding problem, a polynomial algorithm exists for solutions 2 by n, but beyond that, there is no algorithm yet found, according to Wikipedia at least. Anyway, I hope that this has been an interesting expansion on the previous video, and again, if you want to see the original puzzle that these are based off, or other puzzles like it, check out thinkmaths.co.uk/mathspuzzles. If you have any other questions about this video, have found any more mistakes, or if you have any suggestions about what else I should make a video on, let me know in the comments down below. And as always, thanks for watching.